Hello everyone, welcome to another video in the ISI CMI preparation stuff. It's not just ISI CMI, generally exponential and logarithmic functions are really important. Okay, even in IOQM you will see the logarithmic functions. There are few functions which are in general very important, like these two, and functions like step function, box function, lower ceiling function, so floor function. These kind of functions are really important. We'll talk about it eventually, one class after another. And yeah, so we have this in front of us today. So we all know what is exponential, and exponential is generally very famous. Logarithm might be new for a lot of you, right? So we'll see one by one. It's not tough, nothing is tough in this part. Exponential function, whatever function f of x can be written as a power x, is all exponential function. Now you can see that if a is equal to 1, f of x is simply 1, right? It doesn't matter. And another observation is that we will only deal with positive a's. A should be greater than 0, right? Because if it is negative, we won't be able to take for all real values. We want to define it for all real values, right? I want to take f from real to real, and so to be able to define for all values, we cannot take negative, because if I take, let's say, f of minus 2, f of x to be minus 2 power x, then there is, like, for fraction values of x we are not able to define, so we won't take that. And a few properties of exponential, basic indices properties, right? So a power x into a power y is always a power x plus y. In other words, this f of x into f of y is equal to f of x plus y. This kind of correlation is really important. And a power x whole power y is equal to a power xy. In other words, f of x, how would I say this? This is f of x. Okay, so if f of a of x and f of x, if I do that, then that is f a of x y. So I have to define it like f a of x, right? This is the base, this is the index, we call it index, and that is the exponent. X is the exponent, the power is the exponent. That's pretty much it. That's what we will need to the most part. We know this is basically law of indices thing. And of course, 1 power x is 1, a power 0 is 1. So for all x, this is for all x, and this is for all a, right? So these kind of things are there. And the graph of this is the most important. Okay, that's where the crux of it lies. See, when we are drawing graph, we need to know the value of a. We need to have a lot of information about a. The least we need to know is whether it is greater than 1 or less than 1. Because you see, if I have, let's say, a greater than 1, let's say a equals to 2, I can take f of x to be 2 power x. Okay? And the graph of this would look very simple. At 0 it is 1, okay, and at 1 it will be 2, at 2 it will be 3, 4, right? And at 3, it will be 5, 6, 7, 8, somewhere over here, right? Okay. And what about minus 1? Minus 1, it will be half. Minus 2, it will be even half of that. Minus 3, it will be half of that. Minus 4, it will be half of that. So it's going to tend to 0. So if I connect these dots in a smooth, curvy manner, it will go like that, right? So this is the graph, rough graph of y is equal to 2 power x. This is how the graph is going to look like. Okay? And for every, the graph will be very similar for every a greater than 1. Whenever a is greater than 1, the graph is going to be like this. Okay, how about in yellow color, I'll draw the graph of y is equal to 3 power x. How will that look like? It is also very important that you learn how to compare two graphs, right? So let's do that. At 0 it is 1, so with yellow I'm actually drawing y is equal to 3 power x, right? And at 1 it will be 3, at 2 it will be 9, which will be above whatever that was. So immediately it is way more exponential, like way more steeper than this one. Of course it will be a little bit curvy, it's my bad, probably something like this, right? Right, that will be the 3 power x. And how about here at minus 1, it will be 1 by 3, and 1 by 3 is what is 1 by 3? It is less than 1 by 2, of course. So it is somewhere here. It is somewhere here. So when it is negative, when x is negative, it is below the graph of 2 power x. When x is positive, it is the above graph of 2 power x. So that is the comparison. Now, what about when I take a is less than 1? Right? Let's say is 1 by 2. Then my f of x will be 1 by 2 whole power x. So here is where we will see a little thing, that 1 by a whole power x is 1 by a power x, which is a power minus x. This is how we define negative exponent. When we have a negative exponent, negative power, the exponent will be inverted, right? So this is an important property which we'll use right now, because this will become 2 power minus x. So of course, many of you would have guessed it already. It is just a flip. So at 1, instead of being 2, it would be, at 0 it will be 0 anyways. At 1 it will be 1 by 2. At 2 it will be 1 by 4. At 3 it will be 1 by 8. So it's going to 0 this side. But at minus 1 it's going to be, where is 1, 2. Okay, this is 1 by the way, this is 0. Sorry. So this is 2. At minus 1 it will be 2. At minus 2 it will be 4. At minus 3 it will be 8. So it will be like this. This is the graph of 1 by 2 power x. So it is basically a flip of the graph. Flip of the graph. Y is equal to 2 power x. This is y equal to 2 power x, and this is y equal to 2 power minus x. That's it. This is a flip of this graph. So that you must understand. So this is actually a very important lesson right now, that if you know y equal to f of x graph, however it is, if you are converting it, if you want, you know this is known. Okay, if the graph of this is known, then y is equal to f of minus x. Graph equal to flip with respect to y-axis, right? That is flip with respect to y-axis. That's it. That is the graph. Yeah. And what else? What else do we need here? We will also use something called a modulus function. I hope you know what that is, but if you don't, we will look at it in some other time, right? I will take a separate session on how manipulations in graphs work. So all this will be covered in that, right? Okay. Yeah, so a less than 1, that's how it looks like. Now let's look at what is a logarithmic function. Logarithmic function. First of all, what is logarithms? Function, we will see what that is, but logarithms are defined like this. If a is equal to b power c, that will imply this is equivalent to saying c is equal to log a base b. This is the definition. From here only everything will be sprouted. Okay. The power we can write in terms of a and the base. That's what is our aim. So, for example, 3 is equal to log 8 base 2, right? Because 8 is 2 cubed. And I can take numerous examples. 1000 is equal to 10 cubed. So, again 3 is also log 1000 base 10, right? So, these kind of like whatever power you can think of. So 1 by 2 is equal to log root 2 base 2. This is also obvious because root 2 is basically 2 power 1 by 2. So whatever, it need not be integer, it can be fraction, it can be irrational, doesn't matter. We can always do this. And a log can also be negative. When is it negative? So if I have, let's say, 0.1, 0.01 is 10 power minus 2. So that would imply minus 2 is equal to log of 0.01 base 10. Is this the only one when it is negative? Not necessarily. If you look at it, 10 is equal to 0.01 whole power minus 2 as well. So that would imply minus 2 is also okay, minus 1 by 2, sorry. Minus 1 by 2 is equal to log 10 base 0.01, right? So you must notice one thing. So few properties we have already seen right here. So few properties that log a power n base a is equal to n. This is by definition. This is the definition. Basically, we are writing the definition in a different way. That's it. Nothing else. Okay. What else do we have? So one of the most important and very basic property is that log, let's say base is b, a into c, log of a into c base b is equal to log a base b plus log c base b. Okay. So how do we do that? So let's say this is equal to x and this is equal to y, right? So proof is, if that is equal to x, what do we have? A is equal to b power x, c is equal to b power y, which implies AC is equal to b power x into b power y, and by exponential function properties, we have that this will be b power x plus y. Logarithm is basically an inverse of exponential, right? It is exactly an inverse of exponential, by the way. So we will see all of that. Since we were talking about inverse functions in trigonometry, I must tell you logarithm is an inverse of this function, exponential function. Okay. So AC is equal to b power x plus y. So what can you tell about x plus y? X plus y is equal to log AC base b. And what was x and y? So we basically have this. Log AC base b is equal to log a base b plus log c base b. That's it. Clear? Okay. What is the other property? What else can we say? There is a base change property, right? So that is one of the very important properties. Log a base b can be written as log a base c by log b base c, right? In other words, we can actually write this as log a base c is equal to log a base b into log b base c. I mean, these two are simply equivalent. I'm just cross multiplying. Cross multiplying. That's it. Nothing else. So how do we prove this? How do we prove this? So let's see. Let's say this is x and this is y. Right? That is x and this is y. That is x would imply that b power x is equal to a and c power y is equal to b. From these two, what do we have? I replace this b over here. So I'll have c power y whole power x is equal to a. That would imply a is equal to c power xy. And that would imply xy is equal to log a base c. Is that clear? Log a base c. And what is x, what is y? We simply have it in front of us. So log a base c is equal to log a base b into log c log b base c. Yeah, this is the property. This is also very, very important property, very useful while doing some manipulations. See, this is not just for ISI CMI. I'm telling you, this particular thing is really useful for both IOQM, for any exam. You should know this function, you should know these properties, right? And one of the most important things is log 1 of any base is 0. Obviously, because b power 0 is always 1. And log x base b is always defined, well defined, only when b is greater than, the base is greater than 0 and the value inside is greater than 0. This is really, really important. Log is well defined only when the base is positive and the value, the input is also positive. Only then we will be able to define, right? Otherwise, we can't have a negative power. Because whatever value this may be, this would imply that b power y is equal to x and base has to be positive, and hence this has to be positive. Although y can be negative, that is there, right? Okay. Now Let's try to draw the graph of it. I think that should be very, very simple. I think I should also talk about when it is negative. When is log a base b negative and when is it positive? You see, inequalities is really important. This I should talk about in terms of uh, both exponential and logarithm, right? Inequalities. You see, is x greater than y? Does it always imply a power x greater than a power y? Always. Does it? When does this happen? This happens only when a is greater than 0. Only then is it an increasing function. You saw in the graph. The graph tells it very naturally. We go back to, this. For x, if I have x here and I have y here, so x is greater than y implies a power x is here and a power y is here, implies a power x is greater than a power y. And here a was greater than 1. That is really important. Otherwise, in this case, if you have x here and y here, okay, maybe I'll take x more, right? A power x is here, a power y is here. So since a is less than 1 and greater than 0, of course I should have greater than 0. That doesn't make sense otherwise. X greater than y would imply a power x is less than a power y. So this is really, really important. That's what I wanted to mention. And it would also imply a power x is less than a power y when a is greater than 1, sorry. A is less than 1, greater than 0. Whenever this happens, right? You should heavily note this. Okay? Okay. And something very similar will happen for logarithm as well. Logarithm also make sure that there is some, change when we have base is greater than 1 or less than 1. So let's see a few examples, right? If my base is greater than 1, let's see, my base is greater than 1. So let's take the base to be 2 again, our favorite number. So if I have 2 log base 2 of x, if x is equal to 2, then log 2 base 2 is equal to 1. Yeah, that is another property, by the way. I should mention it here, that log b base b is always 1. Like, it's not a property really, but obvious stuff. Yeah. And log 2 base 2 is 1. Log 4 base 2 is 2, and so on. But if I have log base 2 of 1 by 2, that will be minus 1. Log 2 of 1 by 4, that will be minus 2, and so on. So one observation is log base 2 of x is less than 0 when x is less than 1. So can I directly take the power and say this? So here actually I can write that 2 power log base 2 of x is less than 2 power 0, because exponential inequality holds, is conserved, because 2 is positive, 2 is greater than 1. So that will imply that x is less than 1. And log x base 2 is positive when 2 power log x base 2 is 2 power 0. And of course, this is also a very important thing to note, please, that okay, it is very important thing to note that base power log a base b is basically a, and this is also following from definition, nothing different. This is basically definition, there is nothing else. Okay, a power x, okay, this is done. This page is really important. This is like very important in terms of inequalities, right? Because logarithmic inequalities also follow from the exponential inequalities. Logarithm can be removed only when there is exponential, like only through exponentiality. Anyways, so here x is greater than 1. Okay, what about base less than 1? If base is less than 1, log base x is greater than 0 would imply b power log base b power x is less than b power 0. It's not about 0 actually, it could be anything. If it is a, it is a. So x is less than b power a. And log x base b is less than a, then x is greater than b power a. These two are to be noted very nicely. I'll also write the generalized version of b greater than 1. If b is greater than 1, then log base x base b, log of x base b is greater than a would imply x is greater than b power a, because b is greater than 1, really important to note. And log of x base b less than a would imply x is less than b power a. That's also to be noted. Is that understood? These inequalities are really important. Now we will see what do we have. Now we will see what do we have. Graph of y is equal to log base b of x. And for now, let's say b is positive. B is greater than 1. I keep saying b is positive. Okay, if b is greater than 1, let's say b is equal to 2, and imagine that at 1 it is always 0. We don't have, since x cannot take negative values, I'm only focusing on this positive x-axis. So at 0 we are not able to define it. We cannot define log of 0 base anything, right? Because actually it tends to, if x tends to 0 plus, log of x base anything tends to minus infinity. Not anything, for b greater than 1 at least, it will tend to minus infinity, right? Okay. So, but at 1 it is 0, I know that. At 2, so I am drawing y equal to log 2 base x, base 2 of x. So at 1 it is 0, at 2 it is 1, at 3, at 4 it is 2, at 5, 6, 7, 8 it is 3, at 9, 10, 11, 16 it will be 4. So you see how slowly it is growing, very slowly it will grow, right? And from here it will keep on going slowly like that. And here at 1 by 2 it will be minus 1, right? At 1 by 4 it will be minus 2. At 1 by 8 it will be minus 8. Something like this it will connect. This is the graph of logarithmic function for base greater than 1. For base greater than 2, nothing much changes. It is again, it's going to be negative of it. So you see, if I have y is equal to log base 1 by 2 of x, do you see something? Okay, let me say this implies that 1 by 2 power y is equal to x, isn't it? And that would imply that 2 power minus y is equal to x. So minus y is equal to log x base 2. That would imply this is simply minus log x base 2. Now we will learn another graphical manipulation. Okay, it's already 30 minutes. Okay, another graphical manipulation, right? Since this was the graph of y is equal to log base 2 of x, with yellow I'll draw this. This I'll draw in yellow, minus of that. So at 1 it will be 1 only, at 2 it will be, instead of positive 1 it will be negative, at 3 it will be, at 4 it will be negative 2, at 8 it will be, and at 1 by 2 it will be positive 1, positive, positive, positive. So it will go like this. It is a mirroring with respect to x-axis. It is mirroring with respect to x-axis. This is how the graph of y is equal to log x of 1 by 2 works. So here we are actually dealing with b less than 1 greater than 0, right? So here we are actually dealing in a very important thing, that if we know, if y is equal to f of x is known, graph known, then y is equal to minus f of x, the graph is mirror with respect to mirror or flip, whatever, flip with respect to x-axis. So you remember previously what did we say? If this is known, then y is equal to f of minus x will be a flip or mirror with respect to y-axis. And in the previous function, in the previous video where I talked about inverse trigonometric function, we also saw that y is equal to f inverse of x is a flip or mirroring with respect to y equal to x line, right? Here also we will see that if I have y equal to 2 power x, that will simply imply x is equal to log base 2 of y. So these two are mirror of each other. X and y, if you replace them, if I take x is equal to 2 power y, and that would imply y is equal to log base 2 of x. So these two functions, these two are mirror over y equal to x. This is coordinate geometry stuff, a little bit of coordinate geometry, but yeah, that's how it is. Okay, so we'll see how that is so. If I look at the graph of both, exponential goes like this, and I'll draw y equal to x in blue, right? This is y equal to x. This is y equal to 2 power x, let's say. And then that would imply yellow, that this is the graph of y equal to log base 2 of x. Okay, so I know this is not very perfect, but close to what you may imagine, right? If I am allowed, I'll do it again. Array. I'll do it again. Something like that. Anyways, that doesn't matter that much, but the idea is clear, I hope. Yeah. Okay. But this is not accurate at all because I am taking for in general sum A. I'm not talking about base 2 because base 2 actually intersects y equal to x. Does y equal to 2 power x and y equal to x intersect? Yeah, 2 power x will be equal to x many times. Yes or no? Not many times. Do they? Let me know in the comments. So that's a tricky one for you. Okay. When does that happen? When does this happen? So this is you can use Desmos and everything to draw this and see. Okay. And for what about base less than 1 greater than 0? For them also, it will be very much like that. It was like this, no? And the other one was right. And this is, yes, this is y equal to x. And this is y is equal to log b of x. This is y is equal to b power x. These two are, yes, they are reflection over the y equal to x line. So that's all for today. I hope you learned something and we'll meet you soon. Bye-bye. Take care.